Afternoon. Continuing on with the discussion of flip-flops. We first bring up timing diagram for SR flip. So were there any questions about the operation of the SR flip-flop and or the timing diagram? Have any questions? Let's introduce a few more terms, new terms. And the first one we're going to look at is the clock signal. And we briefly spoke about the clock signal. So let's see how it's implemented. If you have a SR flip-flop, and well, any kind of flip-flop for that matter, and you wish to apply a clock signal, we use the AND gate to implement the clock signal. Okay, so that is shown right here. So our standard SR flip-flop comprises of these two NOR gates, right? We add a AND gate in front of both of those. Combine one of the inputs of each gate, and that would be known as our clock signal. There in the center. Okay. So the clock signal, if you look at the truth table, is required to function right. If you look at this last state, what do we see? When the clock is 0, it doesn't matter what the inputs are. When the clock is 0, the output does not change. It remains in the previous state. Okay. So when the clock is 0, output does not change. It remains Qn minus 1 state. Okay. The clock must be present for logic high, logic 1, in order for the flip-flop to function. Otherwise, the output does not change. When the clock is present, these states, it functions exactly as the SR flip-flop. Function as the SR flip-flop. Right? And 0, 0, it's Qn minus 1, and it's 0, 1, output is 1, and it's 1, 0, output is 0. In both cases, clock is present. Clock is present. Works as a normal SR flip-flop. Clock is absent, 0. Remains in the previous state. The inputs do not matter. Clock is required to function. Clock is present. It functions with a normal SR flip-flop. Clock is absent, then the inputs do not matter. Output remains in the previous state. In addition, if R and S are both 0, then the clock does not matter. Clock 0, output remains in previous state. The clock is 0 or 1 is not. And the 1 1 is still the same, not allowed. It's unpredictable. It's a race to the output. Output could be 1, output could be 0. Excuse me, output could be 1 or output could be 0. We would not be able to predict. Okay, so that state is still not allowed. All right, any questions? All right, so let's see how it works. You have an AND gate, and one input of each AND gate is connected together, and we refer to that as a clock signal. For an AND gate, if one of the input is low, meaning 0, output will always be 0. Logical AND is a multiplication. So if one of, even a single input of that AND gate is 0, the output will always be 0. So if clock is 0, output of both AND gates are always 0. Right? So the output of the SR flip-flop would not change. It would remain exactly the same. Hence Qn minus 1. If the clock is 1, then whatever we apply to R and S input is going to be sent to the output of the AND gate. And then it functions as a normal SR flip-flop. That makes sense to everyone? Okay. All right, more questions. Remember that the clock in sequential circuits to keep everything in sync. So if the clock is present, see the circuit is synchronous. Clock is absent. The circuit does not have clock. Obviously, all modern computing devices, but not in modern, all computing devices are kept in sync by a clock signal. Right? CPUs to GPUs, processor, graphics processor, memory, memory access, storage, everything is kept in sync by a single clock signal. So then let's look at two more inputs here. Those are known as the preset and clear. Preset and clear. Preset here is All right, so we have these two. Preset, as the name suggests, would set the output to 1. And clear, as the name suggests, would clear out the output. And so it sets the output to 0. Hence the name clear, it clears out the output. It's shown in the truth table right at the bottom. If clear is 1, right, meaning the clear input is active, then it doesn't matter what happens in the rest of the circuit, the output will go to 0. If preset goes to 1, doesn't matter what happens in the rest of the circuit, output goes to 1. Hence the name is preset here. One important thing you would note about these two inputs is that they would never be high at the same time. Okay. They would never be high at the same time. They're not Harold and Kumar. If you haven't seen that movie, you should. It's amazing. So the preset is 1. Clear must be 0. And if clear is 1, then preset will be 0. So let's look at how it would work. I'll read it. Okay. All right. So SR flip-flop had 2 NOR gates, which are right here. Right. So those don't change. That operation remains the same. The clock was implemented by using 2 AND gates. Now the preset and the clear are implemented using OR gates. Go on. And what is the truth table for an OR gate? It's a summation, right? A logical OR is a summation. So if even a single input of an OR gate goes 1, the output will always go 1. So if preset goes 1, output of the OR gate, which is Q, will be 1. It doesn't matter what you have with the other input of the OR gate. 1 plus 0 gives you 1, and 1 plus 1 also gives you 1. Right? So if you go preset as 1, output Q goes to 1. At the same time, that output Q is fed as input to that NOR gate, which is right here at the bottom. In a NOR gate, both outputs must be 0 if we want the output to be 1. If even a single input to a NOR gate is 1, then the output would be 0. A NOR gate is the opposite of a OR gate. So 1 plus 0 will give you an output of 0. 1 plus 1 will also give you an output of 0. So again, we start here. Preset goes 1, and clear at the same time must be 0, of course. So if preset goes 1, that gives us Q as 1. That QS1 is fed back into the input of the NOR gate. If a single input of a NOR gate goes 1, the output of the NOR gate goes 0. And that 0 is fed into the OR gate. 0 and 0 gives us Q0 and 0. Let's take a pause while you follow through the steps. Let me know if you did the sequence make sense? Yes.
What's the benefit? What's, I'm just trying to understand.
So the larger picture, the question you asked is, why are we doing all of this? Right,
Yeah.
preset and clear. So there are many implementations. So one example of where this can be applied is when we implement a counter circuit. So there is a counter circuit that we'll look at later on in this chapter, perhaps even today. So counter circuit will count 0, 1, 2, 3, 4. In binary, it would be 0, 0, 0, 0, 0, 0, 1, 1, 0, 1, 1, 1, 0, 0, and so on and so forth. So at any point in time, if you want to interrupt that and you want to preset the output of the counter to 0, 0, 0, that's when you would use, or instead of 0, 0, 0, you would want to set it to 1, 1, 1. Count up or count down. You see those small timer circuits, timer circuits. Those small timers, the handheld timers that you might have seen in the labs. One of the functions in there is a switch where you can count up or you can count down. Right? Nowadays, everything's digital. So in smartphones, you just set a timer to count up or stopwatch to count up or timer to count down. So if you want to count down, you would set the value at a certain point. Then you want the output to be high. If you want to count up, you want to reset it to 0. So in both cases, you will do preset and clear preset. Okay. You want to count up, press a button, everything goes to 0. And that's one implementation, one example where you would use. Okay. Question about the operation or question about anything else? All right, then let's quickly look at what happens when the clear input is set to 1. When the clear input is set to 1, preset is set to 0. Output of the OR gate here gives me Q0 as 1. That 1 is fed back as input to this NOR gate. The output of that NOR gate would go to 0. And then 0 and 0 put together would give me Q as 0. Again, clear goes 1. Output Q goes low. Right. And preset goes 1, output Q goes 1. Hence, preset and clear. Okay. The rest of the time, it functions as a normal clock, SR clock. Okay. Let's see. The 3 other inputs we've seen: clock, preset, and clear. Clock is present. Clock is implemented or present in every sequential logic circuit. In the lab, you'll be working with a few digital chips, digital ICs. I think one of them is a counter, a flip-flop. Another one is a NAND gate. And in there, you would see often, you'll see output Q, you'll see output Q0. You'll also see a clock input signal. There will also be set, preset, and clear inputs. So in the lab, we are performing the experiments. If you look at the pinout diagrams, you will come across all of these inputs. Okay. All right. Next, let's look at what happens. What happens when a clock signal goes low or high. Okay. So when the clock signal goes low or high, there can be a certain ambiguity of what the circuit might be doing. Okay. No matter what the frequency is of your clock signal, the pulse width could result in an ambiguous situation where we may not be able to predict the output of a circuit. Okay. Because the width of the on cycle or the off cycle has a certain value. It could be milliseconds or microseconds or nanoseconds, but the circuit could become unpredictable during that time bit. For that reason, a new development was made, and the development resulted in something known as edge triggering. And the edge trigger refers to the transition between two levels. Okay. The edge trigger refers to the transition between the two different levels. If the transition is from a lower level going towards a higher level, meaning from low to high, meaning a positive transition, it is known as a positive edge trigger or a rising edge. Rising edge or positive edge. Also known as the leading edge. And the transition is from a higher level to a lower level, meaning it's falling. It is known as a falling edge. Falling is also referred to as the trailing. The lagging edge. Okay. Again, instead of the circuit responding to a certain level, it is now responding to the transition. Okay. So from a lower level to a higher level, it's a rising edge or a positive edge or a leading edge. It's transitioning from a higher level to a lower level, it's falling or negative. Okay. The way we implement that is by using this. This triangle symbol that you see inside here. That indicates the rising edge. More importantly, this indicates the positive edge. You want to know how the negative edge is implemented? Actually, note it. Bubble outside. Bubble indicates when you're looking at the pinout of your chips in the lab, keep an eye out for this bubble. Sometimes it's very tiny. When it's a bubble, you need it to negative or the opposite. Okay. So, which brings us to this flip-flop known as D flip-flop. D denotes delay. Okay. Delay means stores data or stores data in memory. Truth table is shown right here. You have the clock input and you have the D input. When the clock level is 0 or 1, the input does not matter. The output stays in the same previous state. Okay. Only when the clock changes state and it transitions from low to high, meaning it's a positive edge trigger. See here the symbol, rising edge. At that point, the flip-flop becomes active, and whatever we provide at the D input is then sent to the output. If you apply 0, you get 0 at the output. If you apply 1, you get 1 at the output. Okay. The D flip-flop stores the data in memory. When the clock arrives and transitions, whatever you apply it at, then to the output. Hence, the D flip-flop. Then it's negative edge. It doesn't matter. Output remains in the previous state. It stores the data in memory. Let's look at an example of a D flip-flop in this timing diagram. Right. So first thing we do here is we identify the edges. Now, we can solve this for both positive and negative. I'm going to solve this for a positive edge trigger flip-flop. So let's say the question being asked was, we have a positive edge trigger D flip-flop. Given the clock signal, and you're given the D or delay signal input, what is the output? So the clock input. So the clock input, let's identify where the transition occurs. At 2, 6, 10, and 14, we have the negative or the falling edge. At 4, 8, 12, and 16, I have the positive or the rising edge. So edge 4, 8, 12, and 16. Negative edge transitions occur when it's 2, 6, 10, 14. Other than that, the output should not change. Now, we are not given any information about the previous state or the current state, basically. Right? We don't know, so we can assume. Let's just assume that it is 0. Say until the clock transitions from low to high, which is right here at this point. Positive edge trigger at 4, the output is going to remain at 0. Right? You're assuming the state of the flip-flop output is 0. You can assume it to be 1, doesn't really matter. If something is provided, then you note it down. If it's not provided, you assume whatever you want. Now, once the first positive edge arrives, the input D is sent to the output. So at 4, the output is 1. So output goes high. Make sense? Okay. Then the next positive edge is at 8. At 8, the output is 0. Okay, output is 0. Because the output is 0 at 8, this. Then it stays at that point until the next positive edge at 12, and the output goes high at 12. Then finally at 16, then the output drops 0. Steps make sense? So, as we have already identified the negative edge triggers. Let's practice. Solve the exact same example for negative edge trigger and see what your outputs will be. Okay. This, of course, this here. Then minus 1 previous 6. Left. Okay. Let's look at a flip-flop that resolves. The results are unpredictable state from the previous flip-flops. Remember, in the previous SR flip-flops, if both inputs are high, meaning both inputs are 1 and 1, the output is unpredictable. It could be 0 or it could be 1. So then we have an implementation of a flip-flop known as J K flip-flop. JK flip-flop is the same as a SR flip-flop, except that it provides a resolution for the input states of both J and K being high at the same time. Okay. Functions exactly the same way. Here we have a clock signal. If you notice, there is a bubble. So it's negative edge triggered. Inputs J and K function as a regular SR flip-flop right here. Okay. Say this is the standard SR flip-flop. J is analogous to S and K is analogous to R. If J is 0, output Q is 0. If J is 1, output Q is 1. Set reset. Okay. What happens in 1 and 1, which is right here? That's mostly the output functions as a toggle. Okay. The output toggles. So if J and K are both 1 and 1, the output toggles. If the previous state was 0, then output Q would be 1. The previous state was 1, then output Qn goes to 0. So it toggles between 0 and 1. As long as the clock arrives and both inputs are connected to high or connected to 1, output toggles between 0 and 1 constantly. And there's a name for this kind of flip-flop known as the toggle flip-flop or T flip-flop. And you're going to implement this in the lab. You have in your lab kits, there is a, I believe there's a JK flip-flop. You wire it to function as a toggle flip-flop in the output. All right, any questions? Not the chip registers today, but I we want to show you is the implementation of this JK flip-flop. So if you look at this flip-flop circuit, each one of these JK flip-flops, let's call this flip-flop 2, flip-flop 1, and flip-flop 0. Digital logic circuits, everything starts at 0, right? 0, 1, and 2. This would comprise a 3-bit counter. It's a 3-bit counter. A single bit counter will count from 0, 1. Single bit counter, 0 and 1. That's it, 2 states, 2 possible states. A 2-bit counter will count from 0, 0 to 1, 1. 4 possible states. 0, 0, 0, 1, 1, 0, and 1, 1. A 3-bit counter would go from 0, 0, 0 to 1, 1, 1. 8 possible states, 0 to 7. Okay, this is also something that you would implement. I think there's experiment 7, I believe, in the lab. You then build a counter circuit, count from 0 to 9. 10 decimal skips, right? 0 to 9. Anyway, flip-flop 0, output is 0, it's the least significant bit. Output Q2 is the most significant bit. So truth table will be Q2, Q1, and Q0. The input of both, sorry, not both inputs of each flip-flop, J and K, are connected together to 1. And the output of each flip-flop is fed as clock to the next. That's how it functions as a counter. Okay. The JK flip-flop is functioning as a toggle flip-flop. So the output of each single flip-flop is toggling between 0 and 1. Okay, it's toggling between 0 and 1, and it's negative edge triggered. You see the bubble on the outside. It's a negative edge triggered flip-flop. So every falling edge, the output of the JK flip-flop will toggle. The J and K terminals are connected to high permanently. Okay, in this circuit. So it's functioning as a toggle flip-flop. And let's look at the timing diagram. That will make it easier to explain the operation. Okay. This is the clock input to the first flip-flop, which is 0. Okay. This goes to flip-flop 0. This output Q0 goes as clock flip-flop 1. The output of Q1 goes as clock to flip-flop 2. And you would read the output of the counter in the reverse order. Q2 is the most significant bit. So you read it in this order. Q2, Q1, and Q0. All of them are negative edge triggered. So if we start the first one, we identify all the negative edges. They are right here. And each negative edge of the clock input cycle, the output of the flip-flop toggles. So initially, we clear out the outputs. We begin with 0, 0, 0. The first negative edge arrives. Flip-flop 0 toggles from 0 to 1. So we have then the positive edge arrives. In the positive edge, the flip-flop doesn't change value. Output remains 1. So it remains 1 here. Then the next negative edge arrives, which is right here. The next negative edge, output toggles. It goes from 1 to 0. From 0. It stays 0 until the next negative edge arrives, which time output toggles and goes to 1. And then that cycle continues. Does that make sense? First one. The output is only going to toggle when the negative edge of the clock arrives. And it'll stay at that output for every subsequent positive edge. It'll only toggle when the next negative edge arrives. So the frequency is now cut in half. If the frequency of the first one is 4 kilohertz, let's just say 4 hertz. The frequency of this is 2 hertz. It's now cut in half. Time interval is doubled. the frequency is half. But then this Q0 output is fed back as the input to flip-flop 1, the second flip-flop. And because it's fed as clock to flip-flop 1, you identify the negative edges right here. Okay, initially we cleared out the output, so everything is at 0, 0, 0. Flip-flop 0 goes to 1. When it transitions to 0, which is right here, the output of flip-flop 1 toggles and goes high. So this remained at 0. Now it went to 1. Yes. The output of each flip-flop is used as the clock for the next one. Each one of them is a negative edge trigger. So each flip-flop will not change value, will not toggle until the previous flip-flop output goes from high to low. So each subsequent flip-flop, we try to find the negative edge. It only transitions when the negative edge arrives. It remains high here. Output Q1 goes as clock to flip-flop 2, which remains at 0, 0, 0, 0 until the first negative edge trigger arrives, and then output goes to 1. Next negative edge arrives, output toggles and goes to 0. If we read the output from Q2, Q1, and Q0, you would get 0, 0, 0, 0, 0, 1, 1, 0, 1, 1, 1, 0, 0, all the way to 1, 1, 1. When the output goes to 1, 1, 1, the negative edge sends everything to 0. So the counter resets, goes back to 0, 0, 0, which is what we expect. Sequence makes sense. It's the connection of the output as clock to the next flip-flop. So the effect of the original clock cycle ripples through the entire chain down to the last flip-flop. Hence, it is known as a ripple counter. Okay. Frequency for this will go to 1 hertz. This will go to half a hertz. And again, we can add a 4th, 5th, 6th, 7th, 8th, as many flip-flops as we want, and keep increasing the number of bits for that. Right. All right, so let's see. Time's actually off. So. All right, questions? Yes.
Would it work like pretty similar without a volume trigger using a positive edge?
Yes. So the question being asked is, would it work exactly the same? If instead of a negative edge, it would be a falling, instead of a negative edge, it would be a rising or a positive edge. The answer is yes, it will work exactly the same. So again, as practice, if you, for your own understanding, you can create a timing diagram for when it is a positive edge. You can also do it by setting everything as 1, 1, 1, but that's a count down. This is a count up counter. You have a count down where everything is set to 1, 1, 1, and then it counts down all the way to 0. That would be a different kind of connection. Anyway, we'll end class here today, and we'll pick up here again on Friday.
Thank you.